So here's an exponential decay graph. This time it's the potential difference. So it's the potential difference across a capacitor as it decays over time. Now, how do we test that graph to make sure it's an exponential? Well, there's a couple of ways. And the first way is to make sure of what we talked about in the last section, which is the constant ratio property of an exponential graph. So for example, we could have a look at that graph and we could note down points that lie on the line. So for example, if I look at the voltage, the potential difference at the first 5–10 second intervals, then I can just read them off the graph. Now obviously I've arranged this, there's 200 volts at the beginning, obviously I've arranged this to be quite nice numbers. You know, at 10 centimetres the line goes through 100 and so on, and at 20 seconds it goes through 50 and so I can just read those off the graph, and I mean you're probably seeing the pattern that's kind of cropping up here as I do this. And well, normally the numbers might be quite different to this and so it wouldn't be so obvious, but hopefully you can see that if I call this V0, the initial voltage, V1, V2, V3, V4, then remember the constant and so on. Remember the constant ratio property said that in equal time intervals, the potential difference or the current or charge, if it's current or charge we're looking at, have to drop down by the same proportion each time. So I can actually study this and I can say, well, okay, well V1 divided by the initial charge is going to be 100 over 200, which is 0.5. And then I can say, okay, well what about V2 over V1? And I can say, oh yeah, well V2 over V1 is going to be 50 over 100, so that's also 0.5. And I can see that it is indeed falling down by the same proportion every time. V3 over V2 equals 0.5, 25 over 50. So now, obviously my numbers are arranged, but they would, if it was an exponential graph, they would be very close to being the same, if not exactly the same. Okay, good. Well, there's another way of testing for exponentiality, and that is to make use of natural logs. Remember that what we're talking about here is a graph with the equation V equals V0, or initial potential difference, e to the minus t over RC. Now what we can do is we can take logs of this and we can say, oh okay, well, or natural logs, so we can say, well if I take natural logs of the left hand side, I get the natural log of V, and then natural log of the right hand side, I'm going to have the natural log of V0 e to the minus t over RC. And now I can make use of the log rules. I can say, oh well, hang on a sec, on the right hand side I've really got two things multiplied together. And if you remember, log A times B is equal to the log of A plus the log of B. If you're not sure what I'm talking about, you need to go back and check out my couple of little videos on how to deal with logs. So, but hopefully you're happy with that, you've seen that or you know that from maths. So I can actually write there that the log of V0 times e to the minus t over RC is equal to the log of V0 plus the natural log of e to the minus t over RC. So I've just applied that rule. And then of course what we notice now is we say, okay, well there's something special about this, because the natural log of a number is what you have to raise e to get that number. So it hopefully should be clear that the natural log of e to something is just that something. So we can see that I can actually rewrite this one more time, and I can say, well, the natural log of v is the natural log of v0, which is a constant, and then that's just going to become minus t over rc. So I can write minus t over rc there, because obviously minus t over rc is what I have to raise e to get e to the minus t over rc. Hope that makes sense. Okay, cool. So Well, what we do now is we say, okay, well, if this is true, then this is also true. But this second equation can be written in a form which is the same as a straight line graph. I'm just going to rewrite it slightly. I'm just going to write, okay, I'm going to say, let's rewrite it slightly differently. I'm going to say the natural log of v is equal to minus t over rc plus the natural log of v0. And then I'm going to rewrite it one more time, and just to make it really, 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 really clear, I'm going to say the natural log of v is minus 1 over rc multiplied by t, so I'm just separating that out, plus the natural log of v0. And then I'm going to see how it relates to the equation of a straight line graph, y equals mx plus c. And so we can see that if we were to plot the natural log of v on the y-axis of a graph, and if we were to plot time on the x-axis of a graph, then minus 1 over rc should be the gradient of that graph. And the natural log of v0 should be the y-intercept of the graph. So we can go ahead and do that. And so I'm going to add a column into my table. And the column I'm going to add is going to be what I want to plot on the y-axis. I already have the t column to plot on the x-axis. That's what I'm going to plot on the x-axis. So we just need to add in a column for the y-axis. So I'm going to add in there the natural log of v. Now remember, natural logs have no units, but you do have to say what it was measured in inside brackets. So we're saying the natural log of v, which was measured in volts. And I'm going to do a column to continue this table there. So the first one is the natural log of 200, and you can put that in your calculator, and maybe you might want to pause and fill in all the rest of the numbers. Well, I'll just do it to 2 significant figures today. Normally you would want to do it to the same significant figures at least as the voltage, but we're just doing a simple job here. So well, we should get the following numbers, or you should agree with the following natural log numbers. 2.5 there and 1.8 at the end. Great, so now let's plot the graph. Well, I've got my axes ready, handily, and so let's put on the points, and we're roughly going to have something looking like this. At 10 seconds, 4.6, and at 20 seconds, 3.9, and it is indeed starting to look like it's going to be a straight line, which is pretty cool. So at 30 seconds, 3.2, and at 40 seconds, 2.5, and at 50 seconds, 1.8. Well, remember when you're plotting graphs, this is more to do with the practical questions. Make sure that your data covers at least half the paper in both directions. Well, I think I've just about got away with that here. Otherwise you have to think about false origins. But we're just doing a nice, easy job today. So now let's draw on a nice line of best fit there. Well, we might have something, I mean, these points are carefully chosen, so it's going to look pretty good. Just zooming through there. And, well, according to our method, the gradient of that graph should give us minus 1 over RC. So it's a straight line which confirms that it's exponential. And now we can actually use the graph to get the time constant, because the gradient is minus 1 over RC according to our analysis. And so what that means is we can calculate the gradient from the graph. So we'll do that. We'll use a nice big triangle, and there we go. We shall just go down to there and across to about there, and find our change in y and our change in x. So our change in y is looking like 3.8 change in the natural log, and our change in time, our x, is looking to be about 54, let's say. There we go, 54 seconds. And so our m value then is, from the graph, minus, because it's a negative gradient, is minus 3.8, the fall, or the rise is negative, over 54, which gives us 0.07 to 0.70 to two significant figures. And that means that we can find the time constant by reciprocating it and minusing it. And so what that gives us there is 14.2 seconds, because we know the time constant is measured in seconds. So pretty great. We've been able to use a natural log graph to first test exponentiality and then find the time constant. Hey, so why not? Let's just go back to the main graph, the exponential graph, because of course we could find the time constant from there, because we know, and just to confirm that it all kind of checks out, well, we know that what the time constant represents. The time constant is the time for the voltage or the charge or the current to drop to 1/eth of its original value. So, well, the original V0 is 200 volts. So what's 1/eth of 200? Well, 200 divided by E, well, remember that is or you can do it on your calculator, but remember that is going to be 0.37 approximately of our 37% of our original value. And so if we punch that in, well, that's about 74 volts. And so now we can read off how long it takes to go down to 74. So let's have a look. Well, 50, we can just see that 74 is going to be just about here. And we can look, and yeah, with a more or less, that comes down to, and we'd obviously use a nice ruler, but that is about 14. And so sure enough, this confirms that the time constant is approximately 14 seconds. Hopefully that makes sense. Have a go at some questions, and remember, this works for current decay and charge decay too.